Hello students, myself Anmol Jain. I am working as an assistant professor in IT department at Ajay Kumar Garg Engineering College. Today I am going to discuss an important topic of the computer organization architecture, that is the instruction type and format. Second, how the execution of microinstruction occur. So this is an important topic that is generally asked in the university question paper. So if you want to learn the execution of a microinstruction, so please continue watching this video till the last. That will be very useful for you exam. So the computer instruction, as all we know, that the computer perform different type of functions like transfer of data from memory, transfer of the data from the register, or the transfer the data from input output devices. So for each type of functions, the computer has different type of instructions, right? So basically we have divided the instruction in three types of instruction code. That number one, that is related with the memory reference format, that means that are related with the memory related instruction. Second, the register reference format. Second, the register reference format, that means how the data is going to be transferred from the register. Next is, that is third, that is a input output format, that is how the data is going to be transferred from input output devices to CPU or vice versa, right? So basically we have three type of instruction code: memory reference, register reference, and input output reference. So in register reference and input output formats, only one of the lower 12 bit is set. We will see that how we can distinguish these three type of instruction format with the help of an example, right? For example, we are having an instruction of 0 to 15, that means 16 bit long. It is a 16 bit long instruction, right? How the 16 bit will be divided to distinguish these memory reference, register reference, and input output reference instruction, right? So number one, in this first case, we see that is the memory reference instruction. What we see in the memory reference instruction, that 0 to 11 bit, 0 to 11 bit, that means first 12 bits are representing the address of the memory, and bit number 12, 13, 14, that means next 3 bits are referencing the opcode, that which operation is to be performed, and the last 15 bit number 15, that is I, right? So I is, what is the I? We will see that what is the meaning of I. I implies that what type of mode it is. It is a direct mode or indirect mode addressing. So let's see one by one. 0 to 11, 12 bit for the address, 3 bits for the opcode. So what are the possible combination of 3 bits opcode? That may vary from 0000 to 110, or last is 111. So all possible combination of 3 bits are 000 to 111. But what we are allowing only, that is 00 to 110. We are not allowing the last combination of the bit, that is the 111 is not allowed as the opcode. We will see that why this is not allowed. Next is the register reference. In register reference, what we see, that again 0 to 11 bits are representing the register operation, that which operation is to be performed, and last 4 bits are the combination of 0 followed by 3 ones, right? 0 followed by 3 ones. The register reference instruction is having the combination of 111. That's why 111 is not allowed in memory reference, right? Because we have to distinguish these three type of instructions. So if 111 is here, then 111 is not allowed in memory reference instruction, right? Next, in the input output instruction, again 0 to 11, that is the first 12 bits that are related with the input output operation, and last 4 bit pattern is all 4 ones, 1 1 1 and 1. So now we can easily identify just by seeing the sequence of bit that what type of instruction it is, right. So the opcode is, here the opcode is 111 and I equals to 0, either that opcode is 111 and I equals to 1. So just by seeing and analyzing all these formats, I can distinguish the different type of instruction, right. For example, I say that computer create an instruction of number 0 1 1 1 1 1 0 0 0 1 1 4 bits 3 2 5 7 8 9 10 11 12. So suppose computer generate an address or an instruction binary code. Now my question is which instruction it is, whether this is a memory instruction or it is a register related instruction or it is an input output type instruction. So just by seeing the last 4 bits, I can distinguish whether this is a register, memory or input output, right. So what it says, if in this say we see the opcode, this is my opcode. So what is the opcode? That is the 111. So 111 opcode is allowed in triple code is not allowed in memory reference. Memory reference में ये related नहीं है. That means this is not a memory reference instruction. This is not a memory reference instruction, right? So either it may be a register or it may be a input output instruction. So how we can distinguish the register and input output? That is decided by the most last digit. That is this is 0 or 1. If it is 0, that is the I. If I equals to 0, then this is register reference, and if it is 1, then it is a input output instruction. So here this is 0. So which type of instruction it is? Basically it is now register reference instruction. Register reference instruction. So in this way we can distinguish just by seeing the format that which type of instruction it is, right. Next example I take, suppose this is 1 followed by 3 ones and followed by 12 bits. So what is my opcode is 111. So again I can decide that this is not a memory reference, but it is either the register reference or input output reference. So if it is a register reference, then it should be 0. If it is 1, then this is a input output reference instruction, right. So it is asked in the question paper that what are the different type of instruction format and how we can distinguish them, right. So in computers we have a set of instruction which makes or which creates all the possible combinations of operations, right. So instruction completeness, that means we will provide certain set of instructions that will perform all the possible instructions, that we will say that is the completeness. So a computer instruction set is said to be complete if the computer includes a sufficient number of instruction in each of these categories. Sufficient number of instruction means there should be minimum those instructions which can perform all other operations, right. For example, in category of arithmetic, logical and shift instructions for moving data from register to memory and memory to register, we should have sufficient number of instruction. We should have program control and status checking instruction, and we should have input and output type of instruction. So if we have sufficient number of instruction which can perform all these type of operations, then we will say that my instruction set is complete. So arithmetic, logic and shifting, what does this mean? So we have certain instructions for adding, complementing and incrementing the accumulator. With these we can also subtract. How we can subtract? Because we can add, if we can add two numbers, with the help of complementing we can subtract the number, right. So adding, complementing and incrementing is sufficient for making a subtraction operation. If that means if we have no direct subtraction operation, we are still having a complete set of instruction, right? Similarly, and complement. If we have a logical operation of and complement operation, then we can create an AND gate also. We can create a NAND just by using the complement of AND, right? So and we know that NAND is a universal gate or the universal logic operation. So once we have the NAND operation, so with the help of NAND operation, we can create all other logic operation, right? So that means and complement gate are enough to produce all the possible logic operation. Next, we can construct logic and arithmetic shifts from the circular shift operation. So if we have a circular shift operation, then we can create all the logic shift and arithmetic shift. Next, we can construct multiply and divide from adding, subtracting and shifting. So we have the addition, we have the subtraction and shifting operation, then we can also perform the multiply and divide operation, because these are the sequences of the addition and the division operation. Sorry, addition and subtraction operation, multiply and division. While this is complete, it is not very efficient. It would be to our advantage to have subtract, multiply, or an XOR gate. This will provide some efficiency of our instruction set. If we have these additional instruction, if we have these type of additional instruction, but we can have a complete set of instruction just by having minimum set of instruction, right? So these are the completeness of the instruction. Next, the instruction cycle, how an instruction is executed once it is fetched from the computer or the CPU, right? So that is known as the instruction cycle. The instruction of a program are carried out by a process that is called the instruction cycle. Instruction of a program, because a program is made of a number of instructions, I1, I2, I3. These are the different instructions, but each instruction is carried out and it follows a number of steps for the execution. So this consists of three phases. Number one, fetch the instruction from the memory, decode the instruction, read the effective address of the instruction from memory, and third step is the execute the instruction. So basically we have three: fetch, decode and execute. Fetch, decode and execute. These are the three basic steps to execute an instruction. So how this cycle complete? Let's see. First is the fetch. Initially the program counter has stored the address of the instruction about to be executed, and the sequence counter is clear to 0. That program counter is basically, the objective of the program counter is it stores the address of instruction which is to be executed. So program counters transfer the address. Program counter transfer the address. With each clock pulse, the sequence counter is incremented and the timing signal go through the sequence T0, T1 and T2. So in different time cycle, three different operations are performed. So first one, it is necessary to load the AR. AR means address register. Address register that will be loaded with the help of the program counter, because the program counter is having the address of the instruction that is to be executed. So this program counter will transfer its content to the address register. So in clock T0, what is happening? That the program counter is transferring its contents to address register. Now the address is in the address register, right? So program counter will be updated, right? Let's see that how it is going to happen. Second, subsequently, as we fetch the instruction to be executed, we must increment the program counter, right? Once we have the executed the instruction, the program counter should reference to the next instruction that is to be executed. So in next cycle, what happens? The first one, the program counter is incremented. In next cycle, program counter is incremented because program counter has transfer its current data to the address register. Now it is blank, or it should be updated for the next instruction. Second, at the same time, what happens? Address register is having an address, and this M of AR, M bracket AR, it is referencing that whatever be the instruction at memory location which is containing by the AR register has been transferred to the instruction register. आपका जो भी इंस्ट्रक्शन इस एड्रेस पर था, जो AR पे था, वो इंस्ट्रक्शन कहाँ आ गया आपका? इंस्ट्रक्शन रजिस्टर में. That has been transferred into the instruction register, right? So in order to carry out the instruction, we must decode and prepare to fetch the operand. Once the instruction register has the data that we have discussed in the last slide, that the instruction has been fetched, right? So how it will be decoded? How it will be decoded means, suppose this is 0101 and so on. Now it should be decoded. Now it should be decoded means what is the meaning of each bit in the instruction, right? So in next cycle, how it will be decoded? That the bit number D0 to D7, that means D0 to D7, decode IR register 12 to 14, 12 to 14, that is the opcode. 0 to 11, 0 to 11, that will be go into the address register, and this I, that is the 15th bit, that is the I. So once we have received the instruction, that is to be decoded. How it will be decoded? In the same way as we discussed in the different type of format. If these three bits are 111, then either this is a register or register reference, or it is a input output reference. If it is not 111, then this is a memory reference. So it will be decoded like that. This is a memory reference, right? Second, the value of this I, last bit. If it is 0, then this is a direct mode. If it is 1, then this is a indirect mode. Indirect mode, right? So in this way we can decode the instruction. So in this way we have seen that what is the instruction, what are the different type of instructions, and how we can distinguish the different type of instruction with the help of their different formats, and how an instruction is going to be executed by the fetch, decode and execution, right? Next, now we come to the next important word, that is the micro instruction. So if we see that this is made from two words, one is the micro and second is the instruction. That means this is a part of micro instruction, means this is a part of the instruction. That means suppose we are having two numbers, adding two numbers, add R1 comma R2. This is an instruction, right? This is a instruction. But performing a simple instruction, performing just addition of two numbers, adding the contents of two register numbers, itself it has to follow a number of instructions, right? So how these two numbers are to be added, there is a long story behind the scene that we generally do not think about that. So how this operation is to be performed, that is decided by or guided by this micro instruction. That means an instruction is made up of a number of micro instructions, right? So whatever be perform the instruction, each instruction has a background of a sequence of micro instruction. Let's see. So before going into the detail of the understanding of the execution of a micro instruction, we should have certain basic terminology or the vocabulary for this. First is the micro program. I always compare the program, micro program, instruction, micro instruction. So what we see, a program, what we learn the program, this is the set of instruction. Program is what? Set of instruction. Similarly, if I say that what is the meaning of the micro program, that means micro program, generally I write the micro program as a micro, and this micro program is the set of micro instruction. That means program is a set of instruction and micro program is a set of micro instructions. Simple. So this program that is stored in memory, that generates all the control signals required. What is this control signals required? Basically, these control signals are the set of micro instructions. To execute the instruction set correctly, it consists of micro instructions, right? Micro instructions. What is the micro instruction? It contains a control word and a sequencing. As we have an instruction that is a type of a control word that is in the form of bit 0 and 1, that we call as the control word. Similarly, the micro instruction is what? This is a control word. So sequencing of word, information needed to decide the next micro instruction address, right? So sequencing word is something like that, as we have the program counter in terminology of programs. Similarly, sequencing word or the sequencer is used for the incrementing the micro instruction. Next term, that is the control memory, that we also call as the control storage, CS. So this storage in the micro program control unit to store the micro program. So whatever with the micro program we have for an instruction, that will be stored in the control memory. For example, I say that add R1 comma R2, this is my instruction, but this instruction is having a number of micro instruction, and all these micro instruction, set of micro instruction, the set of this set of micro instruction is known as the micro program, and this micro program is stored in the control storage or the control memory. So this is to be understand that each instruction is made up of number of micro instruction, and set of micro instruction is called micro program, and these micro program are stored in control memory, right? Let's take an example that how basically an execution of instruction occurs. So I have taken an example that add R3 comma R1. So what is the meaning of here? It should be clear. What is the meaning of this instruction is that add the contents of register R1, and what is the meaning of this bracket R3? Bracket R3 means that the R3 is having the address where the data is, right? That means where the data is, and store the result into R1. The meaning of this instruction is this, that we add the contents of R1 with the contents at the memory location which is in R3, right, and store the result in R1, right? It should be clear that what is the meaning of the instruction, because once we are not clear about the instruction, we cannot write the set of micro instruction for my instruction, right? So first step, fetch the instruction. So this instruction will be fetched. Second, fetch first operand, that is R1. The contents of the memory location pointed by R3. So here the first operand is, this is my first operand. I will fetch this first operand, and second operand, that is R1, then I will perform the addition, and at last I will load the result into R1. So let's see that how it occurs actually. So this is a complete flow of instruction, how it happens, right? So first fetch the instruction, second fetch first operand, perform addition, and fourth is load result, right? So story begins from here that we are having a single bus system here, single bus system. So this is having different type of registers. One is the program counter. So what happens, the program counter transfer its contents, program counter transfer its contents to memory address register through this bus, right? So how do we write these two micro instructions? Now this is a micro instruction, that how the program contents of the program counter is coming out and are going into the memory address register. So how we write it? So we write it in this form, that the program counter out, that is PC out, comma MAR in, memory address register in. The contents of the program counter comes out from the program counter and it goes into the memory address register, right? Okay, so the data has been come here. What happens at the same time? The program counter must be updated, right? We will see that how it will be updated. Same time, a read operation is performed. What read operation? Once the address has been received, it will read it into memory. The address will be read into memory here. It will try to fetch what the instruction is at this address, right? So at the same time, the program counter will be updated, because program counter is updated once the instruction has been fetched or the read. So instruction has been fetched, so program counter should be updated at the same time, right? So how the program counter is updated, that is again a micro instruction, set of micro instructions. So how the program counter will be updated? Suppose, so program counter should be updated at the program counts. For example, we see that program count is updated by +4. We are just assuming that an instruction is having 4 byte space, right? So program counter should be updated by 4. So how it is going to be happening? That is select 4. So here we come into this point. Here we have a multiplexer and the input is the constant 4. Just I am interested to add +4 into program counter. So this will be selected in multiplexer. It will come here, and the contents of counter out that were transferred into MAR, the same will come into this accumulator, because I want to add +4, and any operation that will be addition or subtraction, that will be done with the help of the ALU only, because the ALU can perform the operation. So how the address will be updated? That means before updating the program counter value, ALU must be updated. Sorry, ALU will be used. So the program counter contains and +4 are going to be transferred into this temporary register Z in. So these 3 small micro instruction, that the select 4 add operation will be selected by ALU, and Z in, ALU will perform the addition operation, and the result will be transferred into Z, register Z. So what we are saying, Z in, right? Z in, the contents will be transferred into Z. So we are differentiating it Z in. Similarly, now the program counter should be updated. So which value will update the program counter? That is Z. Whatever the contents into Z, that should be transferred to the program counter. So again, next step, the contents of the Z, that means Z out, and it goes into the program counter in. So up to this stage, what we have seen, that the program counter has been updated by the next memory location, right? By in. Now the updated address again has been transferred into the temporary register by, because next time again we have to add +4, right? So this has been transferred into by. Next, this is the meaning of WMFC. It is a write memory function cycle. WMFC stands for the write memory function cycle. So one cycle has been completed. That means program counter has been updated, instruction has been fetched. Next, MDR out. MDR out means the data which has been read here has been transferred into read means data has been transferred into MDR. MDR memory data register has been transferred into MDR out, then IR in. This MDR has transferred its data into the instruction register, that is the IR in. Once the IR instruction register has received the instruction, now R3 out, contents of the register R3 out, because now fetching has been start, decoding has been start. Decoding means the contents of R3 will be out and it will be transferred into memory register, memory address register. Whatever the contents in the register, because R3 is containing the address, so the content will be transferred into the memory address register. Now this memory address register will be read into memory, right? Next, R1 out, the contents of the R1, that means my second operand, R1 out, and this R1 comes into the by, that is my temporary register, and again the WMFC write memory function cycle is completed. Next, MDR out, whatever the contents in MDR memory data register, that will come out. Select by, perform Z operation, perform addition operation with the help of this Z in. Now contents of the R1 and contents of the memory address register which was having the address of contents of R3, both has been come, and that will perform the addition operation, right? Addition operation has been performed, that means both the contents has been added and it has been transferred into again Z. Then Z out, Z transfer its contents to the register R1, because we want to store the result into R1, right? So in this way, a number of micro instructions, these are the sequence of micro instructions. So just performing to add operation, we have to follow a number of micro instructions. So this is a cycle for the execution for an instruction which perform a number of micro instructions.